Hello everyone, welcome to this online NPTEL course. This is part of the X-ray diffraction and transmission electron microscopy course, and today we are going to have some tutorials where I would like to give you some numerical examples explaining the concepts which we have covered in the lectures. So, I would like to mention that all of you have to first clearly understand the concepts what we have discussed in the theory classes, and then all these numericals will have direct relation with those lectures. And if you have any queries, you are free to contact us through the discussion forum in the online portal. So, I will just start the some of the numerical problems. So, first one is related to the very fundamental nature of electromagnetic radiation. So, the question is, calculate the wavelength of an X-ray moving with the speed of light having energy of 10 to the power 5 electron volt. So, what is the relation what we have learnt in the lectures? So, you have this relation lambda is equal to Hc by E. If we can use this relation, we will be able to find the answer for this problem, where H is Planck's constant, C is velocity of light, which is 3 into 10 to the power 8 meters per second, E is 10 to the power 5 into 1.6 into 10 to the power minus 19 joule. And if you substitute all these values, you get lambda is equal to (12.43) into 10 to the power minus 12 meters, or 0.01243 nanometers. So, it is a simple problem where you would like to see whether the wavelength is changing with the speed of light which possess this kind of energy. So, we will move on to the problem 2. So, the question is calculate the lambda SWL for the molybdenum when the acceleration potential is 25 kilovolt. So, if you recall the beginning of this X-ray lectures, some of the first few lectures, we talked about this, the wavelength limit, and one can calculate this with this formula. You can look at it, which is given in nanometers. This is an approximation 43 by V, 1.243 by V. So, you have voltage given. So, it simply substitute this value here, and then you have lambda SWL is equal to 1.243 divided by 25 is equal to 0.049 nanometer. So, this is another simple problem where you can find out this wavelength limit for the molybdenum. We will slowly move on to the next concept. So, the question is, draw a schematic showing the variation of atomic scattering factor F with respect to sin theta by lambda for a copper and aluminum respectively in the same graph. So, the idea is to illustrate the scattering factor of these two metals and then how they are compared. So, that is the idea. So, let us put this. This is sin theta by lambda. So, the copper atomic scattering factor varies like this with the sin theta, whereas your aluminum is varying like this. So, this is again just to give you an idea of how this atomic scattering factors are compared between two. So, I hope you will be able to recall the concept of atomic scattering factor and its significance when we have discussed in the X-ray class. where we talked about the intensity of the X-ray radiation after diffraction. We talked about the significance of this, and this will be useful in explaining that concept. So, you can verify the class lectures. So, now we will move on to other important problem. The question is, calculate the structure factor F for sodium chloride crystal. So, if you recall the lectures on this structure factor, so we have first discussed about atomic scattering factor and then how that is influenced by the atom, specific atoms in giving the total structure factor of a given crystal system. We have solved a few problems in the lectures, and if you can recall. So, this, if you can try to calculate this, in fact this is already solved in the lecture class if I am not wrong. Nevertheless, we would like to recall and then try to redo that. So, the first step is we will write an expression for structure factor F, which is summation of all the individual atomic scattering factor of this form. So, now we can, what is the crystal structure of NaCl? So, if we can write those atomic positions in the unit cells, it will be sodium atoms So, it will be in the a cubic lattice, and then you can see that sodium atom will be in these positions, and similarly we can write chlorine atom positions. So, they are all exact positions of these two atoms in the cubic lattice, and then you just substitute this whole thing in this, and then you will get an expression like this. So, since we are talking about individual atomic scattering factor, it should be a small f. into exponential pi I h plus k plus L into 1 plus h plus k plus so you will, I have not given all the steps, but this is an expression you will arrive at if you substitute each one of them and sum it up and take the common factor out, you will get the expression like this. And then we can now write a condition if h, k and L all are even, then f is equal to 4 times f Na plus f Cl, and we have another condition if h, k and L all are odd, then it is 4 into f Na minus f Cl, and we have one more condition, f is equal to 0, that means the structure factor is 0 if h, k and L are mixed. So, you have three conditions here. If HKL all are even, then the structure factor is 4 into FNA plus FCL. If HK and L are all odd, then F is equal to 4 into FNA minus FCL. Your structure factor is 0 if HK and L they are all mixed indices. So like that you can calculate that for other crystal systems, and some of them have been shown in the slides during the lecture hours, and you can practice it for simple systems. You can take simple cubic and body centered cubic, face centered cubic, and some other simple compounds like this. So, you can follow. So, this is one type. So, now we will move on to some of the applications Bragg law. So, what we are going to do now, look at some of the ideas of interpreting experimental X-ray diffraction data for metals with cubic crystal structures. The reference for this exercise is from Foundations of Material Science and Engineering by W. F. Smith and J. Hashmi. So, we look at some of the parameters or calculation procedures on interpreting this X-ray data. So, we know then Bragg equation. We will start with the Bragg equation. Lambda is equal to 2d sin theta, and we can write lambda is 2a sin theta divided by square root of h square plus k square plus l square. So, this is, you can substitute the expression for d, that is a by square root of h square plus k square plus l square, and then we can also write some of the basic rules. So, these are the rules determining the diffraction planes in the cubic system. If it is a BCC Bravais lattice, then the reflection will be present when H plus K plus L is equal to even, and the reflection will be absent if H plus K plus L is equal to odd. This is for BCC lattice. For in the case of FCC Bravais lattice, then the reflection is possible where H, K and L are all odd or are all even, and the reflection will be absent if H, K, L not all odd or all even. So, using this rules, we can tabulate some of the specific Miller indices, so that we can interpret them easily. I will write few of these values on the board. So, what I have done here is putting this all possible HKL values for the simple cubic system that starts from 100, 110, 111, 200, 210, 211, and then you will have a few more possibilities, then 220, 221, 310, and if you can square all of them and then write this summation of this indices. So, you will see that they will all come under this sequence. So, now you can see if it is a face centered cubic lattice or a BC body centered cubic lattice, which are the reflections you will see in an X-ray diffraction according to this selection rule. So, in the face centered cubic lattice you will see 111, 200, 220 and so on, and BCC you will see 110, 200, 211, 220 and 310 and so on. So, like that if you can keep this table for a reference, it is easy to interpret as a reference. So, now we will see what are the simple relations we can take out from this table. So, we had written this relation in terms of lattice constant instead of D spacing. So, you see for from the X-ray diffraction data we can obtain experimental values of 2 theta for a series of principal diffracting HKL planes, but the incoming wavelength and the lattice constants are constant. You can eliminate them and then we can try to get the ratio of 2 sin theta values. So, suppose if you have the samples which you think that you have both FCC and BCC is there as a mixture, to find out the data or interpreting the data coming from such a sample, we can try to use this kind of a relation, assuming that one is coming from A, the another is coming from B. So, the ratio of these two intensities will be written like this. For the BCC crystal structure, the first two sets of principal diffracting planes are 1110, 200. So, like this from this table. So, we can write one square plus 1 square plus 0 square, 2 square plus 0 square plus 0 square is equal to 0.5. So, now we can write from this So, from this analysis, if the crystal structure of the unknown cubic metal is BCC, then the ratio of the sine squared values that correspond to the first two principal diffracting planes will be 0.5. So, we can work out the similar for the FCC. The first two principal diffracting planes are 111 and 200. Then we can write sine squared theta A by sine squared theta B which is equal to 0.75. So, similar to this we can write, if the crystal structure of the unknown cubic metal is FCC instead of BCC, then the ratio of the sine squared values correspond to the first two principal planes will be 0.75 for FCC. So, based on this, all the X-ray diffraction data interpretation, we will solve one problem. We can take it as problem number 6. So, now let us look at the problem. An X-ray diffractometer recorded chart for an element that has either the BCC or the FCC crystal structure shows the diffraction peaks at the following 2 theta angles: 40, 58, 73, 86.8, 100.4 and 114.7. The wavelength of the incoming X-ray used was 0.154 nanometer. A, determine the cubic structure of the element. B, determine the lattice constant of the element. C, identify the element. So, since already it is shown as a cubic, then we have to find out whether it is BCC or FCC, and of course, we have to calculate the lattice constant, and then we also have to identify the element. So, we will solve this using the known relations whatever we have already discussed. So, what we have done now is we have the 2 theta value given here. So, now we have tabulated the 2 theta value, and then from that theta value, sin theta value and sin square theta value. Now, look at the ratios. For the first and second angle. So, you take first 2 angles, if you take 0.1170 divided by 0.235, which is 0.498 is approximately equal to 0.5. So, since it is 0.5, the crystal structure is BCC. Then we can calculate the lattice constant. So, we know the relation So, you can write A is equal to lambda by 2 square root of H square plus K square plus L square So, we can simply substitute this (0.154) nanometer divided by 2 square root of 1 square plus 1 square plus 0 square 0.117, which is equal to nanometer. So, you substitute this into this relation, you get about 0.318 nanometers, that is a value of A. So, since it is lattice constant is 318 and it has got the BCC. So, from the table we can also find out the element is tungsten. Handbook you can find out the element is tungsten. That is from this crystal structure as well as the lattice constant value we can find out from the handbook or a reference table. So, what we have seen in this problem, if you how to use the sin theta value in determining various parameters corresponding to the given crystal system. So, the previous relations they were all used here, and you can also practice some of these problems where the sin theta values are used to determine the crystal system. So, we will stop here, we will continue to solve few more problems in the next class. Thank you.